Rewinding the cosmos 13.8 billion years in reverse, all galaxies and stars eventually collapse back into a single, intensely hot, dense point. This animated diagram illustrates what cosmologists call inflation. In the first fraction of a second of the universe's existence, a peculiar form of high-energy matter threw gravity into reverse, expanding the fabric of space exponentially to create the smooth, uniform universe we observe today. But tracing the universe back to that moment of hyper-fast expansion creates an obvious question. What exactly happened before inflation kicked off? A landmark piece of physics known as the BGV theorem addresses this. By mathematically proving that inflation could not have been going on forever into the past, the theorem establishes that the universe requires a definitive, hard starting point. At that exact origin, the mathematics of physics create what is called a singularity. If you've ever tried to divide a number by 0 on a calculator and gotten an error, you've seen a basic version of this. It's a point where our equations simply break down and output infinite values. This leaves physicists with a major structural problem. Does this singularity mean physical reality actually started there? Or is it simply a glitch in the way human beings write equations? To figure out if the Big Bang was a true dead end, mathematicians look closely at how equations break. In physics, there are two distinct categories of singularities. This globe highlights the first type, a coordinate singularity. Imagine an equation based on dividing by a location's longitude. In Greenwich, England, at longitude 0, that math breaks down completely. But there is no physical wall in suburban London. The math only fails because of the coordinate system we chose to map the Earth. We see this illusion at a black hole's event horizon. Early physicists thought the horizon was a physical stopping point because their equations failed there. But using a different set of mathematical coordinates fixes the error, allowing information to mathematically pass right through. It acts like a curtain you can pull back. The second type is a curvature singularity. Deep at the absolute center of a black hole, density and curvature reach infinity. No change in coordinates can fix the math here. A coordinate singularity is a mathematical error we can bypass. A curvature singularity is a genuine collapse of physical laws. If the beginning of the universe is a curtain, cosmic history extends further back than we currently know. If it is a brick wall, time itself hits a hard stop. 3 researchers recently set out to classify the Big Bang singularity using a specific variable called the scale factor. This spatial grid visualizes the scale factor. It measures how the distance between objects changes as the universe expands or contracts, shrinking down to absolute 0 at the exact moment of the Big Bang. They tested different scenarios for the early universe. They found that if a universe is dominated entirely by dark energy, the mathematical origin acts as a coordinate singularity, a curtain. Under those specific conditions, light rays and physical history can safely pass backward through the boundary. The math holds up, allowing you to see what happened before. There is a catch. Cosmologists know our actual early universe was packed with an enormous amount of physical matter, not just dark energy. When the researchers factored that early matter into the scale factor equations, the math changed. The semi-transparent curtain instantly hardened into a true curvature singularity, an opaque brick wall. The exact physical ingredients of our universe guarantee that its origin point cannot be bypassed with a mathematical illusion. There is no mathematical trick that allows us to peek past the Big Bang. At this brick wall, Einstein's general theory of relativity, our best description of how gravity shapes space and time, completely stops working. This failure provides a highly specific map. It shows us exactly where classical physics reaches its limit. To make sense of the infinite energy levels compacted at the very beginning of time, we have to reconcile the physics of heavy gravity with the physics of the incredibly small, quantum mechanics. The Big Bang remains a mystery, not because time lacked existence beforehand. It remains a mystery because looking past that wall requires a new rulebook for reality, a theory of quantum gravity.